Welcome to the Lifelong Learner Podcast. Join us as we explore the joy of continuous discovery and growth. Subscribe now.
New podcast episodes.
Start with the
Tune in
basics.
now.
What even is data? Then how to describe it visually and with numbers. Then we'll tackle probability, understanding uncertainty, distributions too, and then the core stuff. Using samples to guess about the bigger picture estimation, testing ideas, the hypothesis testing, and finally looking at relationships, like with regression, and how things change over time.
Perfect. Let's jump right in with the absolute bedrock. The sources define statistics as the science of collecting, organizing, analyzing, interpreting, and presenting data. Sounds simple, but that covers the whole process, really.
It does, and it kind of splits into two big streams. First up, descriptive statistics. This is your starting point, just summarizing and showing the data you have. You know, charts, graphs, averages, how spread out things are. It's about getting a handle on what's right there.
Okay, so just describing the info you've gathered.
Exactly. Then the second stream is inferential statistics. And this is where, honestly, the real business power comes in. You take data from a smaller group, a sample, and you use that to make educated guesses, draw conclusions, make actual decisions about the much bigger group, the population, that you often can't measure completely.
So descriptive tells you about your little chunk of data. Inferential lets you sort of project outwards, make calls about the whole market based on that slice.
That's a great way to put it. And like the sources mentioned, this whole field is getting broader, often called data science now. It's all about using data not just to look back, but to make decisions and build models for the future.
And businesses are screaming for this stuff. That 2019 survey they cite makes it clear. Analytical skills, quantitative skills, they're like gold to employers now. And analytics isn't just describing, it's predicting what will happen and even suggesting what you should do.
Right. And to even play in that sandbox, you need the basic building blocks. A variable that's just something you measure, data, those are the values you collect. And super important, the difference between the population, the whole group you care about, all your potential customers, and the sample, the smaller group you actually talk to or measure, like in your survey.
Which brings us to parameters and statistics. Yeah. Parameters are the true values for the population, like the actual average customer spend, maybe call it ish, which you really know. Statistics are what you calculate from your sample, the average spend in your study, call it X. And inference is all about using that sample statistic to estimate or test ideas about the unknown population parameter.
And here's something that might seem a bit academic at first, but it's so important for knowing what stats you can actually use.
Yeah.
Levels of measurement. It dictates your toolkit.
Okay, break that down. Why should I care if my data is, say, nominal versus ratio? What difference does it make?
Well, think about it. Nominal data is just labels, categories with no real order, like sorting products by color. Red, blue, green. You can count them, find the most popular color maybe, but you can't average blue and green, right?
Makes sense.
Then ordinal data has an order, but the gaps between the ranks aren't necessarily equal, like those satisfaction surveys. Poor, fair, good, excellent. Excellent is definitely better than good, but is the jump from poor to fair the same size as the jump from good to excellent? Probably not. So you can rank them, find the median perhaps, but averaging them is kind of questionable.
Okay. But with interval or ratio data, that's different.
Totally different. Now, the differences are meaningful and consistent. Interval data has equal intervals, but no true 0 point. Temperature in Celsius or Fahrenheit is a classic example. 0 degrees doesn't mean no temperature. Ratio data has those equal intervals and a true 0. Think sales, profit, number of employees. 0 means none. This is the data where you can do all the math means, standard deviations, run regressions, using, say, a mean on ordinal data. That's a basic mistake the sources warn you about.
Got it. That makes a huge difference. You wouldn't average job titles. Okay, the sources also talk about how we get the data. Surveys are a big one, and crucially, how we select our sample.
Exactly. Ideally, you want a representative sample.
Yeah.
Probability methods are the way to go there. Simple random sampling, stratified, cluster, systematic. The names sound technical, but the idea is everyone in the population has a known, fair chance of being picked.
But they also warn about the easier ways, the non-probability methods, like just grabbing whoever's convenient.
Which leads straight to a major problem: bias. If your sample isn't like the population, your conclusions will be off. And one sneaky type the sources highlight is self-selection bias.
Oh, is that like the GMAT score example they use, depending on the college major?
Exactly that. If you only look at GMAT scores for, say, economics majors who chose to take the GMAT, maybe because they're already thinking business school, You're not seeing the scores for all econ majors. The sample is biased because the people in it selected themselves, and that choice is probably related to their score. You might think econ majors are geniuses based on those scores, but you're only seeing the ones who are already leaning towards an MBA.
That's a really sharp point for any kind of voluntary survey or sign-up data. Okay, so we have our data, we know its type. What's step one?
We describe it. This is descriptive statistics territory. And the first thing is often to just visualize data. Your histograms, bar charts, scatter plots, tables. These tools help you see what's going on, patterns, trends, weird outliers really quickly.
Yeah, they're great for telling a story, but here's where things can get dicey, right? The sources really stress watching out for deceptive graphs.
Oh, absolutely critical. People can mess with the axes, chop off the scale, use the wrong chart type, sometimes on purpose, sometimes not, and totally warp the message. You really need to look critically at charts, not just glance at them.
Okay, so visuals are key, but we also need hard numbers, numerical descriptions, starting with measures of center finding that typical value.
Right. The most common one is the mean, just the simple average. Add them up, divide by how many. It's like the balance point. But, and this is a huge but for business data, the mean is super sensitive to outliers. A couple of crazy high or low values can yank the mean way off from what feels typical.
Like the income example, they probably use a few billionaires, lift the average income way up, but it doesn't reflect what most people earn at all.
Precisely. And that's why, especially if your data looks skewed or has extremes, the median is often your friend. It's literally the middle value once you sort the data. And the beauty of it, it's robust to outliers. Those billionaires barely nudge the median income.
And the mode. Is that used much?
The mode is just the value that shows up most often. It's less common for, sales numbers, but it's the only measure of center that makes sense for categorical data. Finding the most popular product size or color.
Okay, center gives us typical, but what about the spread? How clustered or spread out is the data? That's variability.
Exactly. Measures of variability or dispersion are just as vital. Two data sets could have the same mean but look totally different, one tightly clustered, one all over the place. Standard deviation is common. It gives you a sort of average distance from the mean.
But the sources seem to really like the interquartile range, the IQR.
Yeah, the IQR is great and maybe not used enough. It's simply the range of the middle 50% of your data, the distance between the 75th percentile Q3 and the 25th percentile Q1. And just like the median, its big advantage is it's robust to outliers. Those extreme values don't mess with it. Plus, it's what box plots are built on, and it gives you that handy rule for spotting potential outliers.
They also mention correlation, denoted.
Right. Correlation measures how strongly two numerical variables are related in a linear way and in which direction. It runs from -1, a perfect negative relationship, through 0, no linear relationship, to +1, a perfect positive relationship. Tells you if they tend to move together.
And this leads us right back to that huge E warning, maybe the most important one in all of stats. Correlation does not imply causation.
Cannot see this enough times, seriously. Just because sales go up when advertising goes up doesn't automatically mean the advertising caused the sales increase. Maybe the economy improved, boosting both. The sources use that classic ice cream sales and crime rates example, both rise in summer. Correlated, yes.
Yeah.
Does ice cream make people commit crimes? No. This mistake is made all the time in business analysis.
Definitely a critical takeaway. Okay, so we can describe data, but business is full of unknowns, right? Uncertainty.
Exactly. And that's where probability comes into play. It's the mathematical way we measure uncertainty, the chance of something happening. Always between 0, meaning impossible, and 1, meaning certain. Understanding the basics like experiment, outcome, sample space, event is the foundation.
And then the rules for combining probabilities, like the addition rule for or, multiplication rule for and, the complement rule for not, and that important one, conditional probability, the chance of A happening given B has already happened.
Conditional probability pops up all over business. Like, what's the probability a customer clicks buy given they added an item to their cart? And it helps distinguish independent events where one happening doesn't change the probability of the other from dependent events.
Bayes' theorem gets a mention, too, for updating your beliefs based on new evidence. So practically, where does probability help in business?
Oh, everywhere. Risk assessment is huge. What's the probability this project fails? What's the chance of a major supply chain disruption? Decision-making, weighing the likelihood of different outcomes if you launch product A versus product B. Forecasting, what's the probability we hit our sales target this quarter? What's the chance this customer will renew their subscription?
And often we describe these likelihoods using specific patterns, right? Probability distribution.
Exactly. These are like mathematical blueprints showing the probability for each possible outcome of a random variable. We've got discrete distributions for things you can count.
Like a binomial distribution. If you have a fixed number of trials, each independent, with only two outcomes, success or failure. Like counting defective widgets in a production run of 50. Or how many people out of 100 respond to a marketing email.
Perfect examples. Or the Poisson distribution.
Right.
That's great for counting the number of events happening over a fixed period of time or space when you know the average rate. Think customer arrivals at a store per hour, or website hits per minute, or even typos per page in a document.
Okay, those are for countable things. What about continuous distributions for variables that can take any value within a range?
The star player here, partly because of its role later with the central limit theorem, is the normal distribution, the famous bell curve. It's symmetric, defined by its mean and standard deviation. Lots of natural phenomena approximate it, and it's mathematically convenient.
But not everything is normally distributed, right?
Oh, definitely not.
Yeah.
You've also got things like the exponential distribution, which models the time between events in a Poisson process, like how long until the next customer calls, or how long the machine runs before breaking down. And the sources list others that are crucial for inference. The t-distribution, which looks a lot like the normal but accounts for uncertainty when you estimate the standard deviation from a sample. You use this all the time in business analysis. Then the chi-square distribution, used for tests involving variances in categorical data, and the f-distribution, which pops up when comparing variances, and in anovia and regression.
Okay, this is building nicely. We can describe data, we understand uncertainty and its patterns. Now, how do we actually use that small sample to learn something reliable about the big unknown population?
That's the essence of sampling and estimation. We sample because looking at everyone is usually just not feasible. Estimation is the process of using your sample data, calculating a sample statistic like the mean or proportion, to make an educated guess about the unknown population parameter.
And this is where that magic thing comes in, the central limit theorem, the CLT.
It really does feel a bit like magic. CLT is incredibly powerful. What it says is basically if you take samples of a decent size, and often decent is just 30 or more, though it depends, the distribution of the sample means will be approximately normal, almost regardless of what the original population distribution looked like.
Yeah, so even if, say, individual customer purchase amounts are all over the place, maybe really skewed, the average purchase amount from lots and lots of samples will tend to follow a bell curve.
Exactly. That's the power. It lets us use the well-understood normal distribution, or the related t-distribution, to make inferences about the population mean, even if the original data isn't normal at all. It's the bedrock for things like confidence intervals and hypothesis testing.
Okay, let's unpack confidence intervals. What are they really telling us?
A confidence interval, CI, gives you a range of values calculated from your sample, and you can say you're, 95% confident that the true unknown population parameter falls somewhere within that range.
So it's not just a single point estimate, which is probably wrong anyway. It gives you a margin of error, basically.
Precisely. It quantifies the precision or uncertainty around your estimate. Instead of just saying, our sample suggests average customer satisfaction is 4.2 out of 5, you say, we're 95% confident the true average satisfaction for all our customers is somewhere between 4.0 and 4.4. That range is much more informative for making decisions. It tells you how much wiggle room there is. It's absolutely essential for reporting survey results, quality control measures, anything where you're estimating a population value from a sample. You can even use the concept to figure out how big a sample you need to get a certain level of precision.
That feels much more honest and useful for a manager. Okay, what about when you have a specific claim or theory you want to test? Like, does our new ad campaign actually increase sales?
That's exactly what hypothesis testing is designed for. It's a formal, structured way to use sample data to evaluate a hypothesis about a population parameter. The sources lay out the standard steps.
Step 1, formulate the null hypothesis. That's usually the no effect or no difference scenario, right? The status quo you assume is true unless the data screams otherwise.
Correct. And then you state the alternative hypothesis, H, or H'er. This is what you're actually trying to find evidence for. So for the ad campaign, H might be the campaign has no effect on average sales. H could be the campaign increased average sales.
Then you choose your significance level, alpha, usually 0.05 or 5%. This is like your threshold for doubt, isn't it? How unlikely does the result need to be under the null hypothesis before you reject it?
Exactly. And alpha is directly tied to the risk of making a specific kind of mistake. This is critical for business.
Let's pause on those errors. They seem really important.
They are. You can mess up in two ways. A type I error happens if you reject H when H is actually true. You conclude there isn't a fact or a difference when really there isn't one, a false positive.
So with the ad campaign, a type I error would be concluding the campaign worked and maybe spending more money on it when it actually did nothing for sales, wasted money, wasted effort. And alpha, like 5%, is the chance you're willing to take of making that specific mistake.
Exactly right. The cost is wasted resources, maybe changing strategy based on a false signal. Now, a type 2 error is the opposite. You fail to reject H error when the alternative H error is actually true. You miss an effect or a difference that really is there, a false negative.
So for the ad campaign, that means failing to see that it did actually increase sales. You missed the opportunity. You might stop a successful campaign because your test wasn't sensitive enough to detect the improvement.
Precisely. The cost here is a missed opportunity, not capitalizing on something that works, not fixing a problem you could have identified. There's often a trade-off between minimizing type I and type 2 errors. Making it harder to commit one often makes it easier to commit the other.
Okay, so you've set up your hypotheses, chosen your alpha, considered the error risks. What's next in the process?
You collect your sample data, then you calculate a test statistic, like a T statistic or a Z statistic. This number basically measures how far your sample result is from what the null hypothesis predicted in standardized units. Then you compare that test statistic to a critical value from the relevant statistical distribution, like the T distribution or normal distribution, based on your alpha level.
Or more often these days with software, you look at the p-value, right?
Yes, the p-value approach is very common. The p-value is the probability of getting a sample result at least as extreme as the one you actually got, if the null hypothesis were true.
So a really small p-value means, wow, this sample result would be super surprising if the null hypothesis were actually correct.
Exactly. It casts doubt on the null hypothesis. The decision rule is simple. If your p-value is less than or equal to your chosen alpha level, PAO, you reject HO. You have statistically significant evidence against the null and in favor of the alternative. If the p-value is greater than alpha, you fail to reject HO. You don't have enough statistically significant evidence to toss out the null hypothesis. Importantly, this doesn't prove the null is true, just that your data didn't provide strong enough evidence against it.
Okay, PAA, reject AGO. Seems straightforward enough, but here we hit another one of those massive pitfalls the sources constantly warn about, right up there with correlation causation. Statistical significance versus practical importance.
Oh, this is absolutely huge. You've got to understand this difference. A result can be statistically significant, meaning the p-value is tiny, it's highly unlikely the result happened by pure chance, but be completely meaningless in the real world. You might run a huge study and find a statistically significant increase in website click-through rate of 0.01%. The math says it's real, but is spending thousands of dollars to achieve that tiny bump practically worthwhile? Probably not.
So the stats might shout, Eureka, but the business reality just whispers, so what?
That's exactly. Always ask, is the size of this effect, this difference, actually meaningful in a business context? Does it move the needle enough to justify action, cost changes? Don't just blindly follow low p-values. Look at the size of the effect, the confidence interval around it, and use your business judgment. This is a critical bridge between statistics and smart decisions.
Makes total sense, and hypothesis testing forms the basis for checking results in more complex methods, too.
Like regression analysis.
Right. We talked about correlation just showing if two numerical things move together. Regression tries to do more, doesn't it?
Much more. Correlation just gives you that strength and direction of a linear association. And remember the mantra, not causation. Regression actually tries to build a mathematical model to describe that relationship. It aims to predict or explain one variable, the dependent variable y, based on one or more other variables, the independent or predictor variables, x. It estimates how much y changes on average when x changes.
So instead of just saying marketing spend seems linked to sales, regression tries to answer, okay, by how much do we expect sales to go up for every extra $1,000 we spend on marketing?
Exactly that. The simplest form is simple linear regression with just one x variable. The model looks like Eddie B0 plus B1x. Here is the predicted value of y, is the intercept of predicted y when x is 0, which may or may not be meaningful. And B1 is the key thing, the estimated slope coefficient. It tells you the estimated change in y for a 1-unit increase in x.
And multiple regression is just more x's.
Yep. Heads how, B0 plus B1 by 1 plus B2 by 2 plus doma dots plus BKXK. Now you're modeling Y based on several predictors simultaneously. The sources point out a few key things you look for in the output from regression software.
Like, does the model actually fit the data reasonably well overall?
Right. A key metric there is R squared. It tells you the proportion of the total variation in your Y variable that is explained by the X variables included in your model. It ranges from 0 to 1 or 0% to 100%. An R of, say, 0.65 means your model explains 65% of the variability in Y. Generally, higher is better, but it's not the whole story. In multiple regression, you often look at adjusted R, which penalizes you for adding irrelevant variables.
And then you need to know if the individual X variables are actually doing anything right.
Exactly. You test the statistical significance of each slope coefficient. The null hypothesis is usually that the true coefficient is 0, meaning that X variable has no linear relationship with Y after accounting for the other variables in the model. A low p-value for a coefficient suggests it is making a significant contribution.
Let's go back to marketing spend versus sales.
Okay. A simple regression might give you predicted sales equals $50,000 plus $3.50 marketing spend. The beyond of $3.50 estimates that for each additional dollar spent on marketing, sales increase by $3.50 on average. The R would tell you what percentage of the variation in sales is explained by marketing spend alone. But again, even if that $3.50 is statistically significant and the R of WR is decent, does it prove marketing causes the sales? No. It shows an association. You need more context, maybe an experiment, to talk causation.
And the sources mention other complexities too, like how to include categorical predictors like region or product type, checking if the relationship is actually curved, nonlinearity, the problem of multicollinearity where your X variables are highly correlated with each other, which messes up the interpretation of individual coefficients, and the need to check if the model's assumptions are met by looking at the errors, the residuals. Ignoring these diagnostics is another way to get misleading results.
Definitely. Regression is powerful, but you have to use it carefully. Beyond regression, the sources touch on a few other really useful techniques. Analysis of variance, or ANOVA, comes up when you want to compare the average values means of 3 or more different groups.
So instead of doing a bunch of separate comparisons between pairs of groups, like comparing average sales across region A vs B, then A vs C, then B vs C.
Exactly. ANOVA tests the overall hypothesis of whether any of the group means are different all in one go, which helps control the overall type I error rate. Then there's time series analysis. This is specifically for data collected over time, daily, weekly, monthly, quarterly, whatever.
Like tracking website traffic over the past 3 years or monthly inflation rates.
Right. The goal is often to understand the patterns within that time series and, frequently, to forecast future values. We often try to break the series down into components. The long-term trend, predictable repeating patterns within a year called seasonality, like higher retail sales before holidays, potentially longer-term cyclicality, like broader economic booms and busts, and the leftover random ups and downs, the irregularity or noise. Forecasting methods like moving averages, exponential smoothing, or the more complex ARIMA models try to capture these patterns to predict the future. ARIMA, for instance, often requires the data to be stationary first, which loosely means its basic statistical properties aren't changing over time.
And the business value of good forecasting.
Oh, it's immense. Think inventory planning, staffing levels, budgeting, capacity management. Getting forecasts even slightly more accurate can save or make a lot of money. But, like any model, forecasts are based on past patterns continuing, which isn't guaranteed. Big pitfall. Placing too much faith in a forecast without understanding its uncertainty or checking its accuracy.
Okay, what about chi-square tests?
Those are your go-to tools for analyzing categorical data. One common use is the test for independence. It asks, are two categorical variables related? For example, is there an association between the type of discount offered, percentage off versus free shipping, and whether a customer makes a purchase? Yes, no. Another is the goodness of fit test, which checks if the observed frequencies in different categories match some expected pattern or distribution.
And lastly, they mention non-parametric tests.
Yeah, these are really valuable alternatives when your data doesn't meet the assumptions of the standard parametric test, like t-tests or ANOVA, especially the assumption of normality. If you have rank data, or very small samples or data that's clearly not bell-shaped, non-parametric methods provide a way to still perform hypothesis tests. They're often useful for analyzing survey data with rating scales.
We have definitely covered a ton of ground here, from the absolute basics of data all the way through some pretty sophisticated modeling techniques. It really brings home that applied part of applied statistics in business and economics.
That really is the core message from these sources, isn't it? It's not just theory. It's about rolling up your sleeves and using these statistical tools to tackle real business questions with actual data. The emphasis seems to be on understanding why you're doing something and what the results mean in practice, not just plugging numbers into formulas.
And knowing what tools help you actually do it. The sources definitely feature Microsoft Excel pretty heavily, right? Since it's everywhere in business. They show how to use its built-in functions and the analysis tool pack for descriptive stats, correlation, regression, t-tests.
Yeah, Excel is the accessible workhorse, but they also acknowledge the bigger guns, mentioning R, as a powerful, flexible, open source option, especially popular in data science and academia now. And they might nod to others like Python, Stata, eViews, maybe SQL for the data management side. The point is, you'll be using software, so understanding the concepts behind the clicks is key.
But as we've said like a dozen times now, just having the software doesn't cut it. You need the critical thinking to interpret the output correctly.
100%. And to actively avoid those common statistical pitfalls we've kept highlighting. To recap the big ones, don't make misleading graphs. Don't misinterpret confidence intervals. Remember, the confidence is in the method, not that any one interval is guaranteed to contain the true value. Don't read too much into a non-significant result. It doesn't prove the null. Maybe your study just lacked power. Don't worship R squared without checking model assumptions and practical significance. Don't assume normality if your data clearly isn't normal. Never, ever infer causation from correlation alone. Be careful with regression check assumptions. Don't predict way outside your data range. Don't blindly trust forecasts. Use the right test for your data type. And always, always ask if statistical significance translates to real-world practical importance.
And the sources also make a point about using these powerful tools ethically, right? Stressing academic integrity, avoiding misrepresentation.
It's a crucial underpinning. With great data power comes great responsibility.